So today we're going to talk about a couple of the last topics from Unit 2, and that's going to be formal charge and resonance. So we're talking about N2O, nitrous oxide. Anybody know what nitrous oxide is? Anybody know what nitrous is?
Is that laughing gas?
It is laughing gas. So you probably had it at the dentist office if you had your wisdom teeth out yet. If you haven't had your wisdom teeth out yet, you'll get to see what it is. It is also used as a street drug. I don't know what you guys are, your generation's calling it, but it used to be called whippets. Anyway, this is a highly regulated gas because you get a hold of a tank of it, it's worth a lot of money. So dentist office is where you usually find this nitrous oxide. Dinitrogen monoxide is the stock naming system for it. So it says, draw all the possible resonance Lewis structures for nitrous oxide, N2O. Calculate the formal charge of each atom in the Lewis structure. Based on the formal charges, indicate which Lewis structure is most favored and which Lewis structure is least favored. This comes straight from the AP exam. So N2O, we're going to start the same way we always do, which is adding up the number of valence electrons. So you've got each nitrogen has 5, and then oxygen has 6, for a total of 16 electrons. We will represent exactly 16 electrons in this structure. Let's do needs minus owns divided by 2 in order to get the number of bonds, which was how we learned it the first year. So needs is how many electrons do I need to be happy? And every element needs 8 electrons except for like hydrogen and helium and some of our exception ones like beryllium and boron and so forth. But everybody else, carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, chlorine, doesn't matter what you ask, they need 8. So each nitrogen needs 8 and oxygen needs 8. For a total of 24. That's what we would need in order to be happy. Needs minus owns. Owns is the number of valence electrons. So divide it by 2 because that's the number of electrons that are in a shared bond. And that tells us that we have 4 bonds in this structure. Now N2O, usually they give you the structure of this, but in general, when we're trying to pick out the central atom, we're going to try to get the one that is the least electronegative in the center. And in this case, nitrogen's in the center. It is less electronegative than oxygen. Resonance structures mean that there's more than one reasonable possibility for the structure of this. So I'm going to draw you all 3, and then we're going to calculate the formal charge to figure out which one seems the most reasonable. So let's bond them together. That uses up 2, 4. So 16 minus 4, we have 12 left over. Now, if I give each of the nitrogen and the oxygen on the outside 6, they'll be happy, but the nitrogen on the inside will not. And we've already calculated we have 4 bonds. So let's start with the most reasonable one. The most reasonable one would be, oh, nitrogen loves its triple bonds. So now I've used 2, 4, 6, 8. I've used another 4. And I have 8 left over. Nitrogen in the middle is happy. This nitrogen wants 2 more electrons, and this nitrogen wants 6 more electrons. I'm going to go down here and I'm going to draw another possible structure. We'll use our knowledge, the fact that we know that oxygen loves to have a double bond or 2 bonds. He's got 6 valence electrons. If he can get 2 more, he's got his 8 he's happy with. We'll give the other 2 here. And then this, we're using 8, so 16 minus 8, we have 8 left over. Let's satisfy the outside elements. That's another possible structure for N2O. The last one down here, the only other possible distribution for 4 bonds between them is to have a triple bond here, single bond here. This is also 16 electrons, so it is a possible structure. So how do we know which one's the real one? We're going to calculate something called formal charge. So the charge on the ion is the oxidation state. The charge on oxygen is usually -2. The charge on magnesium is usually +1. So it is related to, but not exactly the same as formal charge. So formal charge, our formula for formal charge is going to be the number of valence electrons that an atom has minus the number of non-bonding electrons minus 1/2 of the bonding electrons. And this is going to be logical to you because we're going to try to figure out what the formal charge is, meaning how many valence electrons do we have? How many do I own by myself, which is non-bonding or lone pair electrons? How am I sharing with somebody else? If I'm sharing them, I only have half of the possession of them. So that's why it's 1/2 of the bonding electrons. So let's try this. This is for each individual atom in a bond. So the first nitrogen, the formal charge, is going to be 5 valence electrons. This one right here, minus 2 non-bonding or lone pair electrons, minus 1/2 times 6 bonding electrons. So you'll see the formal charge on this one is going to be 0. So everybody follow where I got those numbers from. Okay, let's do the second nitrogen. It has 5 valence electrons, and then it has 1/2 of 8 bonding electrons. So +1. The formal charge on nitrogen here is +1. Now let's do the formal charge on oxygen. It's going to be 6 minus 6 minus 1/2 times 2, or -1. So the formal charge is -1 for this oxygen, +1 for this nitrogen. This tracks because oxygen's more electronegative. It is more likely that he has a negative charge. So this is an okay structure here. This fits all of our criteria. Now let's do the second one here. So the formal charge on this first nitrogen is going to be 5 minus 4 minus 1/2 times 4. So that'd be 5 minus 4 minus 2, or -1. Formal charge on the second nitrogen would be 5 minus 1/2 times 8, or +1. Formal charge on oxygen is 6 minus 4 minus 1/2, 4, for 0. So in this structure, -1, you want the total to be as close to 0 as possible. So this one is not too bad. Now let's do this last one. Formal charge of nitrogen is 5 minus 6 minus 1/2 times 2, or -2. I can see I got problems already because nitrogen's the less electronegative, and it's got a more negative charge. Let's do the formal charge on the second nitrogen, which would be 5 minus 1/2 times 8. or plus 1. Formal charge on oxygen is 6 minus 2 minus 1/2 times 6, or plus 1. This is less favorable because oxygen is more electronegative, and this is a lot of non-zero. So I would say the formal charge on oxygen being plus 1 and nitrogen being minus 2, nitrogen's less electronegative than oxygen, so this doesn't make sense, so I'm going to reject this structure. So my two structures that seem to fit the best are these two. Now let's go down and talk about resonance. So I just taught you how to calculate formal charge. Now we're going to talk about resonance, because when you do experimentation on this molecule, you'll see that the bond strength and the bond length are somewhere between these two structures. So if you looked at this at face value, this bond is the shortest with the most energy. This is the longest with the least energy. So this triple bond holds the most energy. These guys are the middle of the road, the double bonds. Triple bonds have the shortest bond lengths and the most energy involved, meaning that it takes more energy to break the bond and you get more energy back when you make these bonds. A single bond is the longest and has the least amount of energy in it. So when you do actual experimentation on these, you get that the nitrogen-nitrogen bond is not as short as a triple, and it's not as long as a double. It's somewhere in between. And this is what resonance is. So if you measure that bond length with a piece of measurement equipment, you get 112.6, which is between a double and a triple. When you measure this nitrogen-oxygen bond, it is not as long and the same amount of energy as a single bond, but it's not as short with as much energy as a double bond. It is somewhere in between the two when you measure them. So this is resonance structure. So sometimes when they indicate this, you're going to see these resonance bonds looking like this. So it's definitely got one bond, and it's definitely got two bonds here. And these other bonds are sometimes written as a dashed line saying that they're somewhere in between the two. And that's what resonance is. I'm going to show you a famous resonance structure next, and it's going to be called benzene. C6H6. You've got, let's calculate how many valence electrons we have to represent first. So we have 6 carbons that each have 4 valence electrons. We have 6 hydrogens that each have 1. So that's 24 plus 6. We have 30 electrons to represent. If we did needs minus owns over 2 for the number of bonds, needs, remember, each of the carbon needs 8. The answer for everybody on the face of everybody on the periodic table, the elements, is 8. So we've got 6 carbons that need 8, and we have 6 hydrogens. They don't need 8, they only need 2 to be like helium. So we have 60 electrons was what it'd take to satisfy everybody. We have 30 That means that we're going to have 15 bonds in this structure. This, in this case, is a ring. So you got 6 carbons, like such. And we'll put the 6 hydrogens on the outside. Hydrogens are always dead ends, so they have to be on the outside of a molecule, like such. Now let's bond them together. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 bonds. I have 3 left over. 12 bonds or 24 electrons, and I have 6 electrons left over and 3 more bonds to represent. So this is what you're going to get. 2, 4, 6 electrons. This is the structure of benzene. Here's how you're going to see this indicated in a organic class. It's going to be drawn like this. And how we're going to indicate resonance here is that double arrow, because this structure and this structure are both just as likely. And the reality is, when you take measurements on this particular molecule, it's going to have bond lengths that are all equal, bond angles that are all equal, meaning that the real structure is somewhere between these two. So this is how you indicate resonance here with this double arrow and drawing both structures, one in the beginning of the arrow, one on the end of the arrow. The other thing you can do is use the dashed line for all of these bonds to indicate that there's no difference between this bond and this bond. They measure the same length, they have the same energy, it costs you the same energy to break them. The bond angles are identical. This is a symmetrical molecule, totally nonpolar. Its name is benzene. It's also a super famous organic chemistry, what we call functional group. Now, just a little intro to organic, the way we draw structures. At every single turn, there's a carbon here. And carbons make 4 bonds, exactly 4 bonds. If there's not 4 bonds on carbon, in a hydrocarbon like this, the missing atoms are hydrogens. Because when we're talking about drawing these huge organic molecules, you don't want to have to draw every carbon and all the hydrogens bonded onto them. You would be there all day. So organic chemists, we love a shortcut. This is your first introduction to a shortcut. Okay, any questions about formal charge or resonance?